Hello everyone. So in this video, we'll be discussing a continuation of the multiple integrals, but this time we'll be discussing triple integrals. So if you weren't able to watch the double integrals video discussion, you may watch that from my previous videos. So basically, this is just the same process with how you integrate multiple integrals in double integrals. So here, we have some examples of evaluation of definite triple integral. So the same again with the double integration. We have to start with the inner. We have to start with the inner integrand. Okay. So from here we have integral of 0 to y plus z. That is, we have xyz of dx. And since we are deriving in terms of x, meaning to say y and z are constants. So since that is constant, you can put that out. Then what we have left here is y plus z x dx. And as we know, the integral of x dx is just basically equivalent to x squared over 2. And we have the limits from 0 to y plus z. So after that, since this is a definite integral, we'll be substituting the upper limit to our variable x subtracted by the lower limit. So we have y z times y plus z squared over 2 minus 0. Okay, so expanding this is square of a binomial, so we can expand that. We have yz, y squared plus 2yz plus z squared all over 2. Okay, so after that, let's simplify this further. We can put 1/2 outside. We have yz times y squared, that is y squared, y cubed z plus 2yz yz, we have 2y squared z squared plus yz times z squared is yz cubed. Okay, so we have now simplified our result for the first integration. Now we'll move on to integrating the second integration. So we have 0 to z, then we have integration of dy. So we have 0 to z, and then we have this as our new integrand. So we have 1/2 is constant, we can just put it out. We have y cubed z plus 2y squared z squared plus y z cubed dy. And since we are only integrating in terms of y, so meaning to say only z here, all the variables z are treated as constants. So we have y to the 4th z over 4 plus integral of y squared dy is y cubed over 3. So we have 2y cubed z squared over 3 plus y dy, that is y squared, but we still have the constant z cubed, so you have to copy that, and that is over 2. And our limits are from 0 to z. Now, substituting the limits to our variable y, we have 1/2 z to the 4th z over 4 plus 2 z cubed z squared over 3 plus z squared z cubed over 2. So if you would simplify this, z to the 4th and z that is equivalent to z to the fifth over 4. Plus, we have 2z cubed times z squared, that is equivalent to z to the fifth over 3. Plus, we have z squared times z cubed, we have z to the fifth over 2. So as you can see, they are the same, z to the fifth, z to the fifth, z to the fifth. So we can just combine them together. So we have 1/4 plus 2/3 plus 1/2. Basically, that is equivalent to, sorry, we have minus 0 for the lower limit, minus 0 for the lower limit. And again, we have 1/4 plus 2/3 plus 1/2, that is equivalent to 17 over 12 z to the fifth. And since we have to multiply it by 1/2, 17 over 12 times 1/2 is equivalent to 17 over 24 z to the fifth. But we are not yet done since we still have one integration left, which is in terms of z this time. So we have to integrate it again, but our integrand now is 17 over 24 of z to the fifth. So we have integral of 0 to 1, 17 over 24 z to the fifth dz. 17 over 24 is constant, so we can put that out. So we'll just integrate z to the fifth dz, wherein integral of z to the fifth is just equivalent to z to the sixth over 6 from 0 to 1. So substituting, we have 17 over 24 of 1 to the sixth over 6 minus 0. So basically, 17 over 24 times 1 over 6 is equivalent to 17 over 144. So this is now our final answer. Okay, so we are now on our second example. We have here evaluate from 0 to pi over 2, 0 to 4 sine z, and 1 to y plus 4 of x raised to negative 3 halves dx dy dz. So again, first thing is we have to derive the inner integration or inner integrand. So we have from 1 to y plus 4 of x raised to negative 3 halves dx. And since we are integrating with regards to dx, so meaning to say we can integrate the x raised to negative 3 halves. So integral of x raised to negative 3 halves, the power will be added by 1. So this will become x raised to negative 1/2 over negative 1/2. That is from 1 to y plus 4. So substituting the limits, we have this will become negative 2x raised to negative 1/2. We have 1 to y plus 4. Substituting negative 2 times y plus 4 raised to negative 1/2 subtracted by negative 2 times 1 raised to negative 1/2. So this would become negative 2 times y plus 4 raised to negative 1/2 minus this one. So this would become positive 2. Okay, so after that, we can factor out the common, which is negative 2. So we have y plus 4 raised to negative 1 half. And what is left here is minus 1. So this is now the simplified answer of our first integration. So we'll proceed with the second integration, which is in terms of dy. So we have dy and we have 0 to 4 sine z as our limit. So we have negative 2, put that out because it's constant. So we have 0 to 4 sine z. Then we have this y plus 4 raised to negative 1 half minus 1. That is in terms of y. So we'll segregate this. So this would become integral of 0 to 4 sine z times of y plus 4 raised to negative 1 half dy minus 0 to 4 sine z of dy. Okay, so after that, we can already integrate that. Having u is our y plus 4 and du is just dy. So, meaning to say we can just use power formula to our first integrand. So, we have negative 2 times y plus 4, negative 1 half plus 1, that is positive 1 half over 1 half, minus this one would be y, that is again from 0 to 4 sine z. Okay, so if we would distribute negative 2, this would become negative 4 of y plus 4 raised to 1 half. This would become positive 2y from 0 to 4 sine z. Substituting the limits now, we have negative 4 of 4 plus 4 sine z plus 4 raised to 1 half plus 2 times 4 sine z. Subtracted by the lower limit, we have negative 4 times 0 plus 4 raised to positive 1 half plus 2 times 0. So this is equal to 0. And this one is equivalent to 4 raised to 1 half is 2 times negative 4 is negative 8 times negative sign is positive. So this one, if you would rewrite this, we can factor out the 4, which is common. So what we have left is sine z plus 2 times 4. This would become 8 sine z plus 8. And again, 4 is a perfect square. Square root of 4 is 2 times negative 4. That would become negative 8 of square root of 1 plus sine z plus 8 sine z plus 8. So after that, this is already simplified answer for the second integration. So we'll proceed with the third integration, which is in terms of dz and from 0 to pi over 2. So we have negative 8 is constant, 0 to pi over 2, square root of 1 plus sine z. We have dz plus 8, 0 to pi over 2, sine z dz plus 8, 0 to pi over 2 dz. So as we know, we can just integrate this using basic integration formulas. So this one is a bit complicated. So we'll focus with this one first before we integrate all of the terms or all of the integrands. So, as we know, this is in radical, and in order for us to normalize or to remove the radical, we can multiply it with its conjugate, which is square root of 1 plus sine z, multiply with its conjugate, square root of 1 minus sine z, over square root of 1 minus sine z. Then we have the dz. Again, we'll neglect this one first because we can just answer that directly later on. So we have negative 8 from 0 to pi over 2 square root of 1 plus sine z times square root of 1 minus sine z all over square root of 1 minus sine z. We have dz. And as from the radical properties, if we have square root of a, square root of b, that can be multiplied inside one radical, right? So, meaning to say, we have negative 8 from 0 to pi over 2. 1 times 1, that is 1. Sine z times positive 1, sine z. Sine z, 1 times negative sine z can be cancelled out. So sine z times negative sine z is negative sine squared z all over square root of 1 minus sine z. Then we have the dz. So from the Pythagorean identity, we know that 1 minus sine z, sine squared z is equivalent to cos squared z. So we have square root of 1 minus sine z. Then we have the dz. So cancel the square root and the squared. So what we have left is 0 to pi over 2 cos z square root of 1 minus sine z. And then we have dz. Okay, so if we let u is equivalent to square root of 1 minus sine z, our du would be 1 over 2 square root of 1 minus sine z. Derivative of negative sine z is negative cos z dz. So if we simplify, we have negative cos z dz all over 2 square root of 1 minus sine z. And as you know, if you can observe, we have only cos z over square root of 1 minus sine z. So we do not have negative 1/2. So we have to divide du by negative 1/2, which gives us negative 2 du. So we have negative 8 from 0 to pi over 2, negative 2 du here. And then what we have left is 1 is plus 8 times 0 to pi over 2 sine z dz plus 8 from 0 to pi over 2 dz. So negative 8 times negative 2, that would become positive 16 u, wherein our u is square root of 1 minus sine z plus 8, and integral of sine z is cos z cos z plus 8z, and we have the limits from 0 to pi over 2. Okay, so again, sorry, integral of sine is negative, so this should be negative 8 cos. Okay, so if we would substitute our upper limit, we can have 4 pi subtracted by the lower limit, that is equivalent to 8. So meaning to say this is already our final answer. Because again, if you would still assess this one, this would result to a decimal answer. So it's better to have this as your final answer. Okay, so next one and the last one is this. We have evaluate integral of 0 to 1, 0 to z, 0 to y plus z of e raised to x plus y plus z dx dy dz. So first is we have to integrate the inner part. So we have integral of 0 to y plus z e raised to x plus y plus z dx. And from the exponential properties, if you would recall, if e raised to x plus y, that is equivalent to e raised to x times e raised to y. And since we are only integrating in terms of dx, meaning to say, we can put yz outside because that is constant, right? So meaning to say, this can be broken down into e raised to x times e raised to y plus z. Because again, this does not involve variable x, so we can just have that as constant. So we have e raised to y plus z, integral of 0 to y plus z of e raised to x dx. And as we know, integral of e raised to x is just e raised to x. So we have e raised to y plus z, we have e raised to x, and we have the limits from 0 to y plus z. So we have e raised to y plus z, replacing x by y plus z. So we have e raised to y plus z minus the lower limit, e raised to 0. You cannot neglect this because this is equivalent to 1, right? So meaning to say, e raised to y plus z times e raised to y plus z is e raised to 2y plus 2z minus e raised to y plus z times 1. So that is e raised to y plus z. So this is now the result of our first integration. Okay, so now we'll proceed with the second integration. We'll use different color. We have 0 to z in terms of dy. So we have 0 to z of e raised to 2y plus 2z minus e raised to y plus z. Then we have the dy. In the same case, since we are only dealing with y as our variable, z will be our constant. So we can separate this one as e raised to 2y times e raised to 2z minus e raised to y times e raised to z. We have dy. So, if we separate this, e raised to 2z will become constant, so we can put that out. And then we have integral of 0 to z of e raised to 2y dy minus e raised to z as constant from 0 to z e raised to y dy. So our u here is 2y, meaning to say our du is 2 dy, meaning to say we have to divide by 2. So we have e raised to 2z over 2, and integral of eu is just eu. So we have e raised to 2y minus, sorry, we have from 0 to z subtracted by e raised to z. Integral of ey is just ey from 0 to z. So, evaluating the limits, we have e raised to 2z over 2 times e raised to 2z because we'll replace y by z, and we have e raised to 2 times 0 minus e raised to z. We have e raised to z minus e raised to 0. So this one is equal to 1. E raised to 0 is equal to 1. So what we have left here is 1 half e raised to 2z times e raised to 2z is e raised to 4z over 2 minus e raised to 2z over 2, because we have to multiply this with 1. Minus e raised to z times e raised to z. This is e raised to 2z plus e raised to z. E raised to z times negative 1 is e raised to z. Okay, so if you can observe also, we have the same 2z and 2z, so we can combine that together. We have e raised to 4z over 2, negative 1 half minus 1, that is negative 3 halves, e raised to 2z plus e raised to z. So this is now the simplified answer for the second integration. We'll proceed now with the third integration. So we have integral of 0 to 1 of e raised to 4z over 2 minus integral of 0 to 1, 3 e raised to 2z over 2 plus integral of 0 to 1 e raised to z. Then we have the dz for all the terms. Sorry, forgot to write it. So we can put 1 half outside because it's constant. We have e raised to 4z dz minus 3 halves, 0 to 1, e raised to 2z dz plus e raised to z dz from 0 to 1. So u here is the same, 4z. So du is 4dz. So divided by 4, divide by 4. And then this one, u here is 2z. Du is 2dz. Divide by 2, divide by 2. So 1/4 times 1 half, that is equivalent to 1/8. Integral of e raised to u is e raised to u, where u is 4z. So we have e raised to 4z minus 3 halves times 1 half, that is negative 3/4. E raised to u, where u is 2z. Then for this one is as is. We have e raised to z from 0 to 1. So substituting the limits, we have 1 over 8 e raised to 4 times 1 minus 3/4 e raised to 2 times 1 plus e raised to 1. That is for the upper limit, minus the lower limit 1 over 8 e raised to 4 times 0 minus 3/4 e raised to 2 times 0 minus plus e raised to 0. So if you would evaluate, this is equivalent to negative 3 over 8, all of this. For the upper limit, if you would evaluate, this would become 1 over 8 e raised to 4 minus 3/4 e raised to 2 plus e. Okay? And since decimal answers are not allowed, so we have to um, factor out the common, which is 1/8. So 1/8 e raised to 4. 3/4 divided by 1/8, that is 6 e raised to 2. In order for this to get 1/8, so we can multiply it by 8. Then for this one, we have minus 3. So this is now our final answer. I hope this discussion is clear, and I'll see you on my next videos. Thank you, everyone.